All right, hi everyone. So welcome to MSE 165 CL. I'm Professor Tim Rupert. You can just call me Tim. And what we're going to be doing this quarter is trying to do a laboratory on materials kinetics and phase transformations. Today's really an introduction to how we're going to run the class and how we're going to do things. So it's sort of letting us ease our way into the topic. So the main things we want to cover today are do an overview of the course, talk and work our way through our syllabus and our schedule. We'll talk a little bit about our course goals and how we're going to run the class. We'll do a brief introduction to the methods and the equipment that are used. I say brief because when we are actually running the different lab modules, we'll talk a little bit more about how to perform an experiment on, for example, an optical microscope and what kind of data you get back and things like that. And then we'll also go over general safety that we need to keep in mind, again, which I'll remind you as we work our way through. Okay, so the first thing is it's always good to go through our syllabus and make sure we're on the same page. This is posted on our Canvas website, so you can always get access to it. I just copied and pasted it so we can have a discussion. So in addition to myself, we have a TA, Yunfei Zhang. He's going to be helping us during some of our working sessions and also helping by grading your lab reports. So the structure is always a little bit off now because we're teaching everything remote. So what's going to happen, because you all can't in person be in the lab, it's not possible with the restrictions we have right now. So what we're going to do is we're going to pre-record what's actually supposed to be happening in the lab. I'm going to go in and do it, have a camera there capturing what's happening. I might cut some out if it's just boring and showing me polishing samples or something like that, but it'll basically be able to show you all the steps to work your way through the experiment. And then I can give you the data at the end of it saying, okay, this is the different hardnesses we find for different annealing times or whatever it is. And then the idea is that you can then virtually do this lab by watching the video, seeing how it's done, and then perform the analysis and write up your lab reports. So one thing is we have these 3-hour blocks on Wednesday and Friday. And again, it's a little bit different than usual, but it's helpful to think through and remind ourselves what this means. So really, this is a 1-unit class, which equates to about 3 hours of work. So normally, if you were to be in person, you would come into the lab, and in that 3 hours, you would perform the experiment. And if I'm fair, that would be also the time you need to write up your lab reports and things like that. So, and I'm going to try to stick by that. So I know that with remote teaching, things can become sort of overbearing. Sometimes instructors will expect you to do 10 additional hours outside of the class. It's 1 unit, that's 3 hours. I'm going to try to keep it to that 3 hours of stuff. And if you ever feel like it's not, let me know and I'll do my best to course correct. So the way I think of it is I'm going to keep those 3-hour sessions on Wednesday and Friday. For the first hour, I'll be there. And for the second hour, Yunfei will be there. So we can answer questions, talk about what's going on in the lab, anything. And if you want, you could think of that as that's your work time, and you can carve out that time of your schedule, come in to the Zoom meeting in case you have questions. You don't have to, and just work on things. Now, everything is done asynchronously. I'm recording things, I'm posting stuff online, so you do not have to be there. It's up to you. I'm just offering that as a way to think about what's the right type of time commitment. I won't ask for more than that. And also a way that you could come and interact with other people and ask questions. Because it's a purely lab class, we don't have any required textbooks. I'm going to give you the material you need to perform the labs. I listed these 2 textbooks as helpful but not required, and I'm guessing that most people have these. So Material Science and Engineering is the book you use for Engineering 54, and Phase Transformations in Metals and Alloys. This is the Porter Easterling book that I believe most of you are using for 165C now anyways. So you don't need it, but it will be helpful and help you understand the concepts. So the course website is listed here as well. It's on the syllabus. You should be able to get it through Canvas associated with your UCI Net ID as well. We always are supposed to list the prerequisites. I'm guessing everyone has taken E54 and then some combination of these other courses. In terms of our graded work, the only grade we're going to have here is lab reports. So in theory, I would usually have some sort of participation grade too, but since you can't be there in person doing the lab, I can't really expect that. So just going to be the lab reports. This difference in the value just comes about. I'll show you a schedule in a minute. It's because there's different lengths of the lab modules. Okay, so first one's the shortest, second one's a little longer, third one's the longest. So it's just meant to match up as best as I can with the length of time that we're spending. So there's going to be a lab report for each of the 3 lab modules we have. I will show you in a second a template that can basically guide you on what I expect from that and provide some guidance in terms of what you need to do. So you're not going to be flying blind. I do always get the question of grades, and it's a fair question. But I guess I just want to say that, so my goal is to teach you all the important stuff from this lab and be able to see the application of some of these kinetics and thermodynamics and phase transformations concepts. And I'm happy to give everyone good grades, this is especially true. This is not, some 200-person class. This is a relatively small upper division class. So if everyone does well, I'm happy to give everyone good grades. But I put this little thing here. I need your help too. So you need to work with me. You need to give that effort, again, in that reasonable amount of time I expect, and try to answer the questions I'm asking you and things like that. So in terms of academic honesty, I think it's good to have discussion. So people are definitely welcome to discuss all the ideas, the labs, the data, anything. However, we want people to be submitting individual lab reports in this case. So you need to do the lab report yourself. If you go to our website, you'll find a description of the lab reports, but also a template to provide guidance and how you can do them. I just broke it up and show it on the slide here. The first part of this is a Word document, but the first part of the Word document talks just generally about formatting type of things. So please use 12-point fonts, justify your text, 1-inch margins, things like that. The other thing that's important to look at is I sort of gave a rough guideline for sort of what length of text I would expect. There's no formal rules. I will not immediately give somebody an F if they write 1 page or if they write 50, but I'm just providing guidance for what I think the length would be to answer the questions. And it's generally in that range of 2 to 5 pages. So if you're much less than that, you might not be putting enough detail in. You need to really think about whether or not you wrote enough. If you're more than that, you might be putting in too much detail or writing long, page-long explanations for something that could be explained in a paragraph instead. So that's just the rough guidance to think about. So 20% of the grade is going to be attributed to neatness and clarity. So it's a typed document, so your handwriting can't be anything but neat. But clarity also goes to the clarity of your thought. So are you explaining what you're trying to mean there as well? Or is it this long convoluted type of expression? So that's something it's important to test and get better at for all of us as we do these types of assignments. And then from there, in terms of the content, I basically broke it down into 4 sections. So the first is the introduction and description of the topic. The second is the methods that are going to be used. The third is data analysis and results. And fourth is your critical discussion. So this is the same really flow that you would see in any type of lab report or technical paper. It always has the same type of structure. The other thing I did is I listed some specific questions in there that would be good to answer. And if you think about this, if you can go through and answer all of these completely, you probably have a pretty good lab report put together where you're walking your way through the process and being critical about what the results are. Okay. So in terms of our goals, what we're really trying to do is see the practical application of some important concepts you have learned in the past and are learning now. And this is really understanding the thermodynamics and kinetics of phase transformations. And we're going to look at a few common material systems to do that. So by the end of this lab course, I'm really hoping that we all have a better understanding of phase diagrams and really remembering that tells us what are the expected equilibrium structures inside of our material. We also want to have a better understanding of the kinetics of phase transitions. In other words, what's the time required to form that expected equilibrium structure that the phase diagram tells us? We also want to understand microstructural evolution. So how can that resultant microstructure be manipulated and changed by either changing our processing route or heat treating our material or something like that? And finally, we're going to see a little bit of where structure and property connects. So basically, how do those different microstructures we see and manipulate, how does that affect our materials property? Now, in this case, we're going to use mechanical properties as sort of the stand-in, but you can imagine doing that with different types of properties as well. So getting to what the 3 lab modules are, I'm going to go over them very, very briefly. So there will be a lot more explanation for why I chose this to show this idea, how we're going to work through it, what exactly we're going to do as we step into it. But in lab module 1, what we really want to do is understand how you can run experiments and identify important phase boundaries inside of different materials. And what we're going to do is use the water-sugar system as a nice little model system. So the phase diagram is shown here on the right. And again, I'll talk in more detail later. But the basic idea is it's a very simple system. You, on the left side of it, where it's rich in water, you have one phase, a liquid. So it's liquid plus sugar in a circle. On the right side, you have 2 phases, liquid solution plus some solid sugar as well. So we're going to use this as an idea to see how you would play around with different, manipulating these different thermodynamic variables, either concentration or temperature, and predicting what that boundary would be. In our second module, we're going to look at some of the kinetics of second phase precipitation, and we're going to use the aluminum copper system as a nice stand. So we've learned in our prior classes that this phase diagram tells us for a given temperature and composition, what are the expected phases and what sort of are the composition of those phases and what are the fractions of those phases. But it doesn't tell us how those things form inside of our material. So we're going to start to play with that and use this as a way to understand how, as we move from a single phase to a 2-phase region, how we have precipitation of that second phase. And finally, our lab module 3, we'll dig in a little bit to time temperature transformation diagrams in a slightly more complicated material, steel or iron carbon. And this is just looking at a little bit more complex distribution of different microstructures inside of our material. We've learned about this in classes like E54 already, but basically you can put together iron and carbon in the same amounts, but get very different microstructures if you control how you cool down. And we're going to play with that a little bit and see how that affects different aspects of our microstructure and different mechanical properties. So in terms of the schedule, this is just showing how we're going to work through those different modules. So we're on week 1. We're just doing an introduction, talking about safety, thinking about methods just a little bit. Next week, we'll jump into module 2 and then spend 2 weeks there, 3 weeks on module 3 and 4 weeks on or 3 weeks on module 2, 4 weeks on module 3. What you notice here, and this is, again, the schedule is posted on our website, is that first week, what we're really going to do, introduce the idea, talk about whatever material system we chose, and plan and design our experiment. In some cases, I will be showing you some background preparation you would need to do. So for example, in lab module 2 and 3, we have to take bars of material, cut them into smaller pieces so that we can then heat treat them and see these different reactions. You can't do that in person, so I'm just going to explain the process that I worked through that, and I'll show you what I did. And then we're going to work through and collect the data and then have some time for analysis and interpretation. Now, one thing I mentioned is if you look at those lab report formats, they align with pretty well with the fact that we have the building up of complexity within a given lab module. So for example, it's not that you have to write the whole lab report in the last week of the lab module. What you really should be doing, and what I'll try to help you do, is start writing it along the way. So when we're talking about introducing the module and what material we selected and why and how we designed our experiment, that's the perfect stuff that goes into your introduction and your method section. So sections 1 and 2 can be done early on in the lab module. And then as you get your data, you start to plug that in. So your data might be plugged in week 5 here. And then finally, you do your discussion, analysis, sort of revisit what assumptions you made early on and can have that full discussion. So think of it as we're going to iterate through that process a little bit at a time so it's manageable. Okay, so I also want to go over some safety information. I know this is a little bit weird because you're not going to be in there doing the things, But we teach you all about safety for two reasons. The first is to keep you safe. You'll be watching from a video, so you won't get hurt. So that's okay. But the other thing is we want to teach you about the right safety procedures so that you know this for the next time you go in the lab or for future jobs when you're running experiments later on in your life. So it is still important to remember, and I will try to keep reminding people of the important things we're doing at each stage of the labs. So what's listed on this slide are just general rules for lab experiments. These things are the things that sort of always apply, and then I'll talk about a few different examples when I talk about different equipment we use. So you should never eat or drink in a laboratory. That's a sort of hard and fast rule. Another hard and fast rule is don't use any equipment unless you're trained and approved as a user, okay? And by the way, this goes for me too. So one of the pieces of equipment we're going to use is a hardness indenting tester. And I've used that before, but I hadn't used the one in the undergrad lab in Engineering Tower yet. So I talked to one of our staff members and they trained me on it. So I still have to jump through these hoops too. It's good practice for everyone. A sort of caveat to that is when you're in doubt with any of these things, you should always ask an instructor or a TA. And again, that goes for me. If I am in there and I'm unsure, I should ask somebody that is more experienced than me with that technique. In the labs, we always want to have long pants and closed-toe shoes. That's a sort of campus-wide thing for all the labs we're working. You'll generally want to wear safety glasses if you're working with any hazardous materials and or equipment, and I'll show you some examples of that. You want to have gloves and a lab coat when working with any hazardous materials. There's not a lot of that in our lab this quarter, but there's a little bit. There'll be one thing we do where we have to keep that in mind and be very careful. If you're using chemicals, you have to make sure that all chemicals are clearly and currently labeled with what's in the bottle, what's its concentration, what date was it made, and who's the person that made it. And the reason we do this is this really helps with making sure that things are safe and also disposing of chemicals at some point. So I, in my own lab, have had issues where if somebody graduates and leaves and we don't know what's in that sort of chemical container, you have to treat it as though it's the deadliest substance known to man, and it could be anything. And it's very difficult. Whereas if we know that it's nothing, it's just DI water with a little bit of something else in it, we don't have to worry so much. If you're using volatile or flammable compounds, they need to be used inside of a fume hood. I'll show you an example of that. And basically what we want to do is if we're going to do any procedures that are producing aerosols, you want to have that happen inside the fume hood. The fume hood keeps everything contained and it keeps inhalation of any of these toxic or hazardous materials from happening. If you want to make sure to dispose of waste and broken glassware in proper containers and clean up any spills. Okay, so let's walk our way through some of the pieces of equipment we'll use. And again, I'll talk in more detail about exactly what we're doing with these during the lab modules. But one of the things we'll do when we're working with the water and sugar system is we'll use this heating and stirring plate. It's a relatively simple thing. This plate will get hot and heat up our solution of whatever we care about. In this case, it's this water and sugar mixture. And also there is a magnetic stir bar system. So basically, if I put this little magnetic piece in there and I turn this on, it will spin around fast and make sure everything is mixed, okay? So in terms of safety, generally you wanna make sure you're wearing safety goggles as you're doing this. Even though we're working with something that's relatively benign, sugar and water, this stirring mechanism can cause splashing up, and it might even be hot liquid. So you need to be careful with that. And you also generally need to be careful with this hot surface. So we're working with a water-based system, so we probably won't get all that hot. But in theory, these things can go up to at least a few hundred degrees Celsius, and you could actually hurt yourself on that. So you need to be careful with that. We will also, right behind this in the lab is a fume hood. This is just a picture I took the other day. There's some chemicals in there with secondary containers. We'll be using this in lab module 3 when we will be etching some of those steels that we're making so that we can see the microstructure. When you're working with these chemicals, you want to make sure you wear safety goggles, you want to wear the appropriate gloves, and also wear a lab coat. Another thing we'll be using is a polishing wheel. This will be something where I'm preparing some samples before we test them, and then even cleaning up the surface before we look at the microstructure or do a indent. when you're using a polishing wheel, the way this thing works is this wheel right here, we'll put a plate on it with basically really nice sandpaper and polish down to a very beautiful finish these pieces of metal. This thing can be spinning pretty fast, so you need to make sure you wear safety goggles. Sorry, this is the spinning mechanism could throw something up at you. And you also need to be very careful with your grinding surface. So, you may want to make sure your fingers stay away from it. We'll also be using a box furnace to anneal different samples. Basically, this thing has heating elements running along the inside, and then it's insulated from the outside world. We can set this at different temperatures and leave our materials in there for a given amount of time. So when we're working in that furnace, we want to always wear safety goggles. We want to wear heat-resistant gloves when opening. And we also don't want to reach in there and grab any hot materials and burn ourselves. So generally, we're going to use something like these pairs of tongs to grab our material and do with it whatever we want. We will be using something called a hardness tester. This is shown in the top left here. It's a pretty simple system. So this is a light source here, and then a microscope that you can look through. And there's a place right here you can put your sample. It's zoomed in a little bit here. And when your sample is there, you can either look at the surface with a microscope, or there's a little sharp indenter head that can come down and press into your sample with a known force. And then you can inspect how much damage happened to the surface, and that tells you something about your material properties. So in general, there's no major safety issues with this. Really, you just need to be more careful that you are not doing crazy things and breaking the indenter tip or the microscope lenses. We'll also be using some optical microscopes and looking at surfaces of samples. This is pretty simple. In this case, it's an inverted microscope. So the microscope is pointing up and your sample is facing down. And we can then look at it either with the manually, or we can send the image to a video camera and view it on this computer over here. There's no major safety issues here. Generally, you just want to be careful with the microscope lenses and not damage things. So just to finish up, I'm going to give you a little bit of my background so you know who I am, because we're going to be working together for this lab. So I am from Ohio originally, long way from California. I grew up in a town called Niles, Ohio. It's not known for much, it's a very small town, but it was the birthplace of the 25th president. So there's this museum in my hometown, libraries are named after it, the high school is named after it. I left home many years ago, went and studied mechanical engineering. So I believe everyone here is a materials major, but I didn't know at the time when I went to college that I wanted to study materials. I just knew I liked planes and cars and mechanical things, and that was my interest. And when I moved to Baltimore to go to Johns Hopkins University, that's when I ended up doing undergraduate research with a professor there, Professor Hemker, and started to study bond coat materials, so metal layers that are put into turbine blades so that they can operate at higher temperatures, and got really interested in a lot of the things we're going to talk about in this class. So what's happening with microstructure? I went and did my PhD in material science at MIT with somebody named Professor Shu. And there I studied nanostructured metals and looked at a lot of surface damage in these materials and how they react, and then predicted and tried to engineer better systems. And I've been here at UCI for about 10 years now. So one thing I do is I spend a big chunk of my time teaching, but the other thing I do is I run a research group. I'm just showing one of our recent group meetings. You guys are doing this lab remote. We're doing our own lab systems and meetings remote too. So we're all sort of making the best of an odd situation. But in my group, we deal primarily with nanomaterials. Work with a lot of nanocrystalline materials where the grains are really, really tiny, usually below 100 nanometers. We look at things like how the boundaries between those crystals behave and are organized. We think about how we can maybe segregate or dope those boundaries to control their behavior, and also look at segregation and doping and other types of defects in these materials. And we also do a lot of mechanical testing. Some of it is basically the same version of how we would normally compress and pull on materials, but on the micro scale. So this is basically showing a little compression test, but this pillar is only about 4 microns wide. So for reference, a piece of hair on your head is about 100 microns wide. And then we also look at more complex mechanical behavior, so how thin films wrinkle. This was how bed bugs can be pierced, and also things like wear damage the surface of materials. Okay, so that's it for today. Hopefully we'll see many of you in our what I'm calling our working sessions on Wednesday and Friday, and I'll talk to you all soon.